try another example of formal charge with the cyanate ion. Now, don't get too crazy with the cyanate ion. Carbon goes in the center. So we're going to kind of draw this looking linear, where we're going to go like sulfur, carbon, nitrogen. We're not going to get too nuts, so carbon really does go in the middle. Okay, so carbon likes to make 4 bonds, so let's see if we can draw this by following the rules, huh? Lewis structure. Carbon with 4 valence electrons. Well, nitrogen likes to make 3 bonds, right? 1, 2, 3, and there's 5 valence electrons. So this looks kind of cool. Okay. Well, sulfur, let's see what we can do here. Sulfur's normally got 6 valence electrons, and it normally looks kind of like this, right? 2 pairs and 2 singles. And so I can obviously single bond right here, but then you may be a little worried about that sulfur not having an octet. That's why the charge is -1. So again, like a lot of times when people are trying to learn the polyatomics really early on in the year, they get confused with the charges. You're like, why does this have a particular charge? Because if I add up the charges on sulfur and carbon and nitrogen, you don't get -1. Yeah, it has to do with the structure. In order to give everybody an octet, we need 1 more electron. That's why there's a -1 charge. There we go. And then finally, we should put this in brackets. And then we'd say -1 to show that this was only possible if we had 1 extra electron. Here's one acceptable Lewis structure for the cyanate ion. A single bonded sulfur, a triple bond to the nitrogen. But now again, this is a really common free response style question where they might say, draw at least 2 different structures of the cyanate ion. And they must be acceptable structures. So we have to use the right amount of electrons, and we have to give everybody an octet that needs an octet. Nitrogen and carbon are in the 2nd energy level. They cannot take an extended. Now sulfur could if we had to. Sulfur's in the 3rd energy level. Okay, so I don't know. Like, what if you wanted to try something? Let's just see if something else works. This might be kind of cool. What if we go carbon, double bond, double bond? I don't know. We're just supposed to draw something. Carbon's got an octet. He needs it. Nitrogen needs an octet, so we're going to give him 2 more pairs. And same with sulfur. Let's start by giving him an octet. He needs at least 8. So this is kind of cute. Everybody has an octet. The 2nd order of business is to check your electron count. I would always check your electron count. Let's see what we got here. Sulfur. Sulfur carries 6 valence electrons. Carbon brings 4. Nitrogen is 5. So if we add all those up, we get 15. But since it's a -1, we get to add 1 for a total of 16. So an acceptable Lewis structure needs to give everyone at least an octet, and we have to use 16 electrons. So I mean, for kicks, let's just double check our first structure. It had octets, 2, 4, 6, 8, 10, 12, 14. Yep, 16. That first one is good. 2, 4, 6, 8, 10, 12, 14, 16. This one's good. So we'll make it official. -1. Okay, let's try something else. I don't know. Let's go like, I don't know. What if we flip it? What if we do something like that? That'd be kind of interesting. Carbon in the center already has an octet. Sulfur's got 2, 4, 6. There's your 8. And then nitrogen would need 6 more. That's interesting. Let's say we just kind of did like the opposite of that first structure. We put the triple bond on the sulfur. 2, 4, 6, 8, 10, 12, 14, yeah, I mean 16. -1 charge. Okay, so now let me just show you a couple things that I've also seen in the past. What if the question says draw, 3 acceptable Lewis structures? The first one, the black structure and the red structure, in this case, are different. Even though there's a single bond and a triple bond around the carbon, they're different because the triple bond is to nitrogen in the first structure and it's to carbon in the last structure. So sometimes people will say, oh, but those are the same. The carbon has a single bond and a triple bond. No, they're different in this case because they go to different atoms. But what if you tried this? Sometimes people that'll try. What if they try something like this? Yeah. How about that? We tried two double bonds in that blue structure. Let's go 2 triple bonds, huh? And then let's give this sulfur an octet. Let's give this nitrogen an octet. 2, 4, 6, 8, 10, 12, 14. Bingo, 16 electrons. Do you see what's wrong? Yeah, I used 16 electrons. But look at carbon. Oh no. Poor carbon. That's too many bonds. Carbon can only take an octet. I gave him way too many electrons. This would not be acceptable. So again, they're going to say something like, draw an acceptable Lewis structure. Yes, I used the right amount of electrons, but no, it's not acceptable because you overloaded the carbon. Sulfur could take an extended, but in this case, sulfur really is not the central atom. Don't go too crazy. It really is carbon in the center. Another option. I'll see this sometimes. What if somebody did 2 singles? What if you did something like this? And then we'll load them up, give them octets. Sulfur's all set. Carbon, 2, 4, 6, 8. And then we'll finish off the nitrogen. Everybody's got an octet, right? 2, 4, 6, 8, 10, 12, 14, 16. Whoa! 18, 20. Too many electrons. So be careful of these. Sometimes people are, I don't know, they're just letting the creative juices flow. But you got to be a little bit careful. These would be 2 structures that are not acceptable. You have too many bonds on your carbon in the first, and then the second one, we use too many electrons. So really, I think these first 3 are our best bets. With carbon only being able to take an octet, we're a little bit restricted. We can do the 2 doubles, we can do a single and a triple, and then we can kind of alternate the triple bond. All right, here's the fun part. Let's go formal charge. Let's figure these out. Sulfur normally carries 6 valence electrons. We're going to subtract the amount that we've assigned in our structure. 2, 4, 6 single electrons, and then that single bond is going to count for 1. It's really 2 electrons being shared between sulfur and carbon, but we split them equally. 1 for sulfur, 1 for carbon. Now we go through with the next guy. Carbon normally has 4 valence electrons. I've given him 4. He's got 2, 4, 6, 8 electrons, which is good. He's got an octet. But then we split those evenly between the atoms in the bonds. So 4 of the electrons go to carbon, 1 went to sulfur, and the other 3 will go to nitrogen. Nitrogen normally has 5 valence electrons. we've given him 1, 2, 3, 4, 5. Well, look at that. I like it. I've got low formal charges. I've got some zeros. It gives me a -1, which is the charge on the overall structure. This is looking good. All right, let's try the second one. Sulfur. Normally carries 6 valence electrons. I've given him 2, 4, 6. Ooh, a 0 again. There's 4 electrons that are non-bonding, and then that double bond has 4 electrons, but only 2 go to sulfur. The other 2 go to carbon. Carbon normally carries 4 valence electrons. Oh yeah, we gave him 4. That's a happy carbon. He's got 8, but we split them in half. 4 go to the carbon, 2 for sulfur, and the other 2 go to nitrogen. Normally had 5 valence electrons. We've given him 6 for a formal charge of -1. But that's still not bad, huh? We've got some zeros. We have a -1 overall. If we add up all the formal charges, we get the charge on the ion. Ooh, this is going to be a tough call, huh? Okay, let's do the last one. Let's see what we got here. Sulfur normally carries 6 valence electrons. We gave him 5 for a formal charge of 1. There's 2 non-bonding, and then 3 electrons go to sulfur from that triple bond. Carbon normally carries 4. We gave him 4. 0. Nitrogen normally carries 5 valence electrons. Ew. We gave him 7. 6 non-bonding, and then 1 more from that single bond. Ew. Okay, well, this last structure, I mean, it does give me an overall formal charge of -1. If I add them all up, I get -1, the charge of the ion. But do you think we could rule that one out right away? Because we're supposed to have low formal charges. That's most stable when we have low formal charges. Here I've got like a +1. You know, then I got this nitrogen with a -2. I'm trying to get the most zeros. Let's get rid of it. I'm pretty confident saying that's not going to be the most stable. So now we have to decide between the first two. They both have 2 zeros, which we want. We want lots of zeros. They both give me a -1. So the tiebreaker goes to electronegativity. We want that negative formal charge to be on the atom that would have a higher electronegativity. So if I look at the periodic table, FON, fluorine, oxygen, and nitrogen, have the highest electronegativities on the entire periodic table. That would be something worth noting. I always say that they're fun. Fluorine, oxygen, and nitrogen are small atoms, so there's going to be lots of attraction between the nucleus and the electron cloud. They carry the greatest electronegativities. So in the first one, I've got the -1 on the sulfur. The second structure, I have the negative on the nitrogen. Between these two, this second one is the winner. This is the better structure because the negative is on nitrogen, and nitrogen has a higher electronegativity. Oopsie, electronegativity than sulfur. That's always kind of my tiebreaker. First, I'm looking for lots of zeros. Next, I want to make sure that, they all add up to the charge on the particle. And if it were neutral, the charges should all add up to 0. And then often my tiebreaker will be that electronegativity piece. If I've got any negative formal charge, it should go on the most electronegative atom. Now again, what if the AP test said draw 2 acceptable Lewis structures and use formal charge to say which is best? What if you didn't draw that second one? What if you only drew the first one and the last one? Then you would say, according to the structures that I drew, the first is better. You might not draw the true structure of the ion, or you might not have drawn the best structure, but they're going to say, of the structures that you did draw, which is best, which is most stable. And then I would have said the first one, even though in this case the all-time winner is actually the two double bonds.